Just in previous lecture, that is boosting intuitions, at the end of the case stage we have built the models that look like this kind of models we have built at the end of the case stage, that is if k of x, this is simple, the summations over I is equals to, suppose let's take 0 to k a alpha I into hi of x. These models we have since we have built these things at the end of the case stage that we have already seen. So now the thing is that hix. So the thing is that, so hix. So hix means what? Actually hix actually at the end of the case step, we at the end of the case step we are building the model. We are interested in building the model mk plus 1. That's models are actually built from this kind of data sets. These data sets, these models are actually built from these data sets xi and error I, this from this kind of data sets. And this data, the error I, if you just consider the error I, this error I is actually the residual error yi minus fk of xi. This error is called the s residual error. This error is called the residual error at the end of the stage k. At the end of the stage k, this is the residual error. Okay, and the gradient here, the gradient is called for, actually we are using the, so let's see why these things are called the gradient boosting. What is the main intuitions of the gradient is, so our job is at the each stage, our job is to lose the minimization function, to minimize the loss functions. Okay, so our job is minimizations of the loss functions. This is actual job, and already in the previous series of lectures already we have seen. So the logistic loss, we have using the logistic loss for classification, and we are using the linear loss for regression, we are using the hinge loss for support vector machines. So hinge loss to build the support vector machines. That's another thing to regressions. Okay. So suppose let's take for simplicity, suppose for simplicity we have taken here the for simplicity we have taken here the linear loss for easier of our understanding. For easier of our understanding we have, let's take the linear loss function. Okay, so let's take, so the for linear actually regressions, for we are interested to build the regression model. Suppose let's take, it is also understandable for, if you just easily understand the regression technique, and this concept is easily extendable for the classifications as well. Okay, suppose let's take, we have taken here the linear loss means square loss, or another term it is the square loss term. Already these things we have seen. Suppose our loss functions, we are building that end of the case stage, we have the data x, we have the data yi, and corresponding after end of the case stage we have the functions fk of xi. This one is k, fk of xi. At the end of the case stage we have this data. Okay, at the end of the case stage, and we are now interested to minimize these loss functions. So here loss functions L of x is what? yi minus fk of xi. this square. Okay, this is the actually. And now let's take, now let this term, now let take this term is equals to zi. Let's take, let f a of xi is equals to zi. Let's take. So if just now here regression we have taken the square laws functions. If we just taken these things, just now the derivative these things. So now del of L with respect to del of the functions that we have built at the end of the case stage. Now we are interesting to minimize these loss functions. So we are in derivative these functions this respect to these functions I. Okay. So this means what? This means L of del by del zi. So this means del by del zi yi minus of f a of xi. Okay, if we just derivative these things, so what we will get? We will get minus 1 into 2 or into yi minus f a of xi. That's things we have actually got from these steps. This means what? This means this term means zi. Okay, so actually what we are get from this stage, we will get del L by del d of zi is equals to minus 2 of yi minus zi. Okay, these things actually we will get. Now just see, just we are convert this thing, just this, if you write this thing this way, 2 into yi minus zi. Okay, just I am writing these things in that way. Okay, so this is means what? This is simple, this means it's simple, this is simple, the negative derivative. This is simple, the negative derivative. Okay, and this thing, these things yi minus zi, actually this is the residual error. Okay, just we will already we have seen this thing, these things means actually residual error. Okay, at the end of the case stage, residual error. Okay, residual error, these things. Now the if you omit this thing, just if you omit this constant term, just if you neglect this constant for some time, just neglect this constant. So this, the important idea here is the negative derivative. Derivative actually means for single variables we are using the term derivative, but actually here we have taken the large dimensional of data. Our data, this zi, this L is not a single dimension. So instead of using the derivative term, it will be better for if we use the gradient term here. So these things is actually means negative gradient. Negative gradient. Negative gradient means what? Negative gradient means this is the equivalent to, this is the equivalent to the residual error. Residual or another language, these things is equivalent to residuals, or another language, this negative derivative is called the pseudo residual. Pseudo residual. Why this is called a pseudo residual? Because the negative gradient, just you see these things are actually the error. These things are actually error, and negative here we are using the negative of the gradient, sign of the negative. Pseudo residual means this is a false residual. False means this is not the actual. This gradient is not the actual because you have taken the negative sense. This another language it called the pseudo residual. Pseudo residual. Okay. This is not actual term. Actually we have omitted the negative and 2 here and 2 here, and also the this is and this is the derivative, and also you have taken the negative signs. So because of this negative gradient is called the sometimes called the pseudo residue. Okay. Now the questions is that why, sir, actually we have taken this negative gradient here to minimize the x steps. Why I am not taking the simple residual error? That's already we have seen in the boosting intuitions. Why I am not taking these things? Why I am using these derivative terms? So let's see these things. So what actual term here? Our term is hi of x. This is the actual our functions that we have built for the h stage. After end of the h stage, we have built this model hix, and these models actually built from this data set xi minus error I, and this error I means what? Xi and error I, and this error I means, and this error I means what? This error I means yi minus fi minus 1x. This error I means that yi minus fi minus 1x. Okay. So the error is actually called the, actually we have seen this error is actually called the residual error. These things are actually residual error, but here we are simply using the gradient technique. Gradient, just we are using the gradient to minimize this gradient, negative gradient. Okay, negative gradient. But why actually these things are used? Why actually we are doing these jobs? Okay, so error I is simple the residual error, and also the error that we have seen. Error I is also the same as the negative gradient, means pseudo residual. Both are the error, but here these things are using by simple derivative term, means gradient term, and here this is the simple residual error. But why these things are actually we have doing this in gradient technique? Why these things actually we have need? Why these things actually we have need? Okay, because just if you remember the previous lectures, just simple, just see these things. Actually if you just consider this thing, just if you just consider the random forest, suppose let's take, if you consider the random forest, in random forest what we are doing? We are doing the minimize the entropy value. We are doing the minimize the total entropy value, minimize the total entropy for each decision tree or Guinea impurity, total entropy for all base models. Minimize these jobs we have doing for building the random forest. But if we interested, but if we want no, I'm not want to minimize the entropy, I want to minimize the hinge loss here. I want to minimize the hinge loss. If I want the minimize the hinge loss, so if I just want these things, but these things are cannot possible by simple using the residual, but these things are possible if we consider the pseudo residual, means gradient, negative gradient term. if we just consider these things is possible. Okay, because the pseudo residuals are simply minus del L by del of f I minus 1 x. Okay, these things are actually we are doing, actually we have derivative these things. Here we have taken the square term, square loss. Here we are taking the example, as an example we have taken the square loss. Okay, but if you just taken the hinge loss, you can easily take it, you can easily take the logistic loss as you like. Okay, so both kind of each kind of loss are applicable for the pseudo residuals, but if simply using the residuals, it is not possible by these things that we have seen in the if we in random forest. If we interested to minimize the hinge loss, that is not possible, because in random forest we are we are using the we are build the random forest model for edge decision tree by simply reducing the entropy or Gini impurity. Okay, so these things are the advantage of these pseudo ratios. It let us have any loss function which is differentiable. That any loss functions that are differentiables, then we can easily apply the pseudo residuals for this loss function. But these things cannot be applicable for simple residual technique. These things cannot be applicable for residual technique. Okay, this is the main advantage of the pseudo ratio, nothing else. So in gradient boost, decision tree, in gradient boost decision tree, in simple random forest decision tree, we cannot minimize the hinge loss. But in gradient boost decision random forest, we can easily minimize any loss function. We can easily minimize any loss function. Because of any loss functions, also it will be differentiable. If any loss function it is differentiable, then we can easily minimize these loss functions by simply using the gradient boost technique. So the advantage is that it is super powerful. It is super powerful. These things are called the simple super powerful. Super powerful technique. Okay, and also there have another kind of gradient boost technique that is called the ADA boost. We will see these things in applicable point of view. ADA boost technique, we will see these things. So actually what are actually doing here, actually we have a base model. We have a base models that have high bias, and combining this base model, combining the base model by using the pseudo residual. Pseudo PACUD. Pseudo residual. Combining these things by simple using the pseudo residual. Okay, means del f by del 1 z, sorry z, not it will be x. Okay, by the simple combining these things by using the simple this pseudo residue. Okay, I think the main intuitions and how the gradient boost actually gradient technique are actually work actually applicable by simple taking the any kind of loss functions that is differentiable. The main conditions is it will be first, the main conditions that the loss functions will be differentiable, then we can easily then we can only use the gradient boost technique. Okay, and also we will in details we will see in the next part of the next part of the some videos. We will see these things, how these things are details in mathematical point of view, how these things are actually internally work these things. And another language in stage I, just in another thing in stage I, if we just conclude this lecture in stage I, what we are doing actually in stage I, what we are doing, we have a at the end of this I minus 1 we have the model if I minus 1x, and by using this model we are building the model that will build in stage I. Okay, so these models are, we have the model at the end of the stage I minus 1, and to enter into the stage I we have the model, this model if I minus 1x, and also we have some data that is xi, residual error I, and using this data we have built the model mi. Okay, and this error here, this residual error means simple, that it is a pseudo residual error, pseudo residual error. Okay, this pseudo residual means del okay, that's job we have to do by simple using this. And now by simple the as previously we have discussed, by simple by using this error we have building these models and the same things to build the fi of x, that will help, these models will help to build this model, to build this function. Okay, I think the main motto of these lectures is clear, how actually the gradient boost techniques are internally doing this kind of jobs. I think the main I will give the main intuitions mean behind the reasons. In the next lecture we will see in details the mathematical point of view, how the gradient boost technique actually work in mathematical point of view. Okay, this is the simple the introductions of the gradient boost technique. Okay, we will see this thing in details mathematical point of view in next lecture.